Hello again. Welcome back to those of you who ever find these videos. Or maybe somebody will. Uh, the topic I'd like to get on the two this time is addition, and addition is actually related to one of the things I told you about last time, which is this XOR. XOR. I just want to give a little explanation of what that is. Now, XOR, the logical operation, that is, it just has a meaning in logic, and it's an operation where that has two inputs and one output. So I'm imagining, let's suppose we have two values, AX and BX, and they can be either true or false. Notice I use small letters. The reason I'm using small letters is because these can only be true or false. But these are like one bit, could be one bit of the AX register. And the result of this computation, whatever it is, we'll put in CX. Okay, make sure that's far away so we can see. The definition is just this. If this is called XOR, if both are false, if zero means false, then the answer is false. And if one of them is true and the other is false, then the answer is true. So it has two cases. True. But if both of them are true, then that's different from the usual or, that's false. So what that says is, this thing is true when one or the other of A and AX and BX is true, but not both. If they're both true, this condition is false. Now, the AX thing, the XOR logical operation has some kind of interesting little features. One was I showed you that if you XOR something but itself, you always get zero or false. And that's easy enough to prove because there are only two cases. Either with one bit, either AX is zero, and 0 XOR 0 according to the table is 0, or it's 1. And again, that gives me 0. So that provides a quick means of zeroing out any number of bits. Something like that. If I do an XOR with something with itself, that means it's doing it bitwise. It applies it bit by bit. One is in columns here. So it does this one XOR with this is 0. This one with this gives 0. 1 and 1 gives 0. Oops. And you can see that they're all going to match, and I'm going to get 0. And that's quite quick. It's a much faster way, it turns out. You save 4 clock cycles or something like that. So that's one other interesting little thing about it. But the thing that I'm most interested in is in the fact that, in a sense, XOR, this logical thing we're looking at, if we could make a circuit that could do that, then we've almost solved the problem of addition. Because when you add two things, usually, if I'm adding two numbers, and if it's just one bit, then 1 plus 0 certainly gives me 1. And 0 plus 0 certainly gives me 0. So far, so good. And 1 plus 0 gives 1. And 1 plus 1 is pretty much what you would get when if you only had one bit. That's what 1 plus 1 is. If there were 2 bits, then you would have to carry. So XOR, I would think, if I was going to build an adding machine, I think I could probably do it if I had XOR, maybe with some other thing. And that's where I started with my logic machine. Excuse me. My adding machine, I should say. And I could have already assumed that XOR was built into the machine, but I'm imagining that this is, 1930 or something, and all I've got to work with are the 3 basic instructions from which everything else can be made. There are only 3. Sometimes people say there's 7, but in fact there are only 3. And the 3 logical circuits that you have to be able to design. You can tell the electrical engineers, please make this. I want not. And I want a thing, I want an object, an electrical circuit, that when I provide an input, A, say, then I want the output to be, so suppose we're talking in voltages. If I provide a plus 5 volts, I don't want this anymore, then I want the output to be 0 volts. And if I supply 0 volts, I want it to do the opposite and flip. So that operation is called NOT. So, and then the engineers get busy working on that problem. The other thing I want is something called AND. I want a thing where if I supply 5 volts, this one takes 2 inputs, call them A and B. So if I put plus 5 volts at A, we'll start with 0. 0 volts at A, 0 volts in B. I want a single output, and it should be 0. Otherwise, if this is 5 volts, and this is 0 volts, I want it to stay 0 volts. But if they're both plus 5 volts, I want this output to be 5. The output's usually labeled Q or something. And this operation is called AND. And lastly, I want another thing that takes 2 inputs and gives 1 output, A and B. If A is 5 volts and B is 5 volts, start with 0 again. If they're both 0, I want the output to be 0. Okay? Now, otherwise, in every other case, I want the output to be 1. So any of these is 5 volts. 5 volts is our representation for 1. If either line is high, then I want the output to be high. So I'm going to skip Q. Essentially I'm saying that if the input here is A, or Q equals not A. Or it should be the opposite. Okay. Now it turns out you can build the entire logical structure of humankind based on these 3 operations. Right up to differential geometry and advanced calculus, logic, your computer, what I'm doing now, everything, every single thing that you can do in logic, you can do with these 3 basic operations. Usually they tell you there are 7, but telling you there are 3. And I'll just give you what they were again. Not, or, and. Those are the 3 things you need. Alright. So, what do I call it? So this was what I was getting at. Here's the usual set of 7 logical operations that are given. But it turns out, first we got not, or, and and that we already have. XOR, I'm going to show you in a minute. I can build from these. And all these other ones are just the not of these ones. So you're done. All you need is the first 3. So let's look at the first 3. Well, over on the right here is not. Basically, it's a transistor. Here's the voltage supply. And a transistor is like a switch. And somebody came along and invented a way where if you supply a voltage to an electrical unit, it can close a switch or open a switch. In this case, if I put charge on this, it will open the switch. So that means when this is high, the switch is open, and this is circuit's open, so this guy is low. And when I open the switch, the circuit closes, and then this guy gets his 5 volts. And this is 5 volts. So that's not. And it's also very easy. In this case, there are 2 transistors of the closing variety, and that one works quite easily. If any one of these, if A or B is low, then one of these switches will be open, and the circuit won't be closed, and so you won't get any output. But if they're both high, on, that closes both the switches, and you get high coming out on this side. So there's and. Or, almost as simple, if you can understand my picture. Here again, I got 2 switches. A and B are the inputs. This is my way of trying to express that it's not connected here. It's hopping over this wire, it's hopping over this wire. And This is OR. Because if you notice here, this circuit closes when either one of these switches gets closed. If this one's closed, then I can follow this path all the way around. Or if this one's open but this one's closed, then I can follow it this way, right? But if both of them are open, I get nothing. So OR is solved. See how easy it is? What about XOR? I had some trouble with this one. Here's XOR, given what we already have. What do you do? Here's our inputs, A and B. You take A and split it up into two things. One, in the first line here, you take naught of A. So if A is high, this one will be low. However, since it's split up like this, this one will have the same value high. Okay? And for B, it's done exactly the same thing, except in the opposite order. Okay? So we have not B and A going into this thing, which is an AND. You know how to make an AND. And not A and B going into an AND. So we have, that amounts to not A and B coming out of here, and not B and A coming out of here, the exact opposite, and then the OR, the result, when we have an OR. And it turns out that that is the same as XOR. Let's see if that's true. So basically, if you wrote this in C code, it would look like this. Let's get them all on the screen at the same time. Yeah, almost. Oh, I think you can see it all. So, not A and B, or not B and A. Okay? Now that you should be able to read it off pretty easily from this. If both A and B are true, then both of these conditions are going to be false. Because one or the other of these things will be false. So they can't both be true. If both of these things are false, it amounts to the same thing. They can't have the same value, or else both of these things are going to be false. However, if they have different values, like let's say, for instance, if A is true and B is false, then even though this one comes out false, because I get false and false, this one will come out true because it's in the opposite order. So B was false, so not B is true, and A was true, so we get true. We flip it around, then this one will be true. So we get exactly from this circuit, the behavior we want. So that's an XOR circuit. We'll have a look at it for a while. Beautiful thing. Alright, how can we make an adder? This is before. Okay. Well, this is my little adder. I didn't look this up because I wanted to try and do it myself to see if I could do it. I'm using the XOR circuit up there that we just saw, and I'm combining it with an AND. And what I'm trying to do is put two inputs in, have the addition occur. Remember I showed you that XOR essentially does the addition part as normal. And what I want to happen is that when these are both 1, I would like an extra output to be 1, called a carry. Now you're starting to see what all this carry stuff is about. So let's see. Clearly the first part's going to work. Let's fill that in there. These are connected. These two, AX and BX, we can go, if we want, we can go find cases. If they're both 0, XOR is 0, and these are connected to here, again, this is going underneath here, and it's not touching the wires. These are going into an AND, but they're both 0, and so this would actually be 0 in that case. Alright. Now let's try putting 1 here. The XOR circuit is going to give us 1. And we put the 2, we put a 1 and a 0 into an AND, and it still end up with 0 here. So far so good. And if this is 0 and 1, it's the opposite. Same argument. But if both of them are 1, then this one will be 0 because of the XOR rule. And 2 1s going through an AND gives you a 1 here. So I've invented an adder. I take AX and BX. The result will correctly come out here, 1 or 0. And what gets left, what gets kicked out the side, is the carry bit, what we call carry. And if I could somehow change this adding machine along, I would be able to do it kind of in a chain, and the whole thing should allow me to add up any number of digits. So, go down here, and I've actually built it. This is what I came up with. Now, this here I'm calling the right carry. So the right carry is coming from another adder that's on the right. And this is the left carry, the thing that I want to spit out of my adding machine. Okay? Now, what I've done here, should have made this more clear. Fix it. Now, these are the adding machines I already built. So, we know how that these things work. And so, each one takes 2 inputs and provides 2 outputs. And what I've done here is I'm imagining that this is the, let's say the 6th bit in a sequence, a chain of all these adding machines, which is supplied with 3 inputs, like when you're adding 2 numbers. There's the 2 inputs from the number you're trying to add, and there may or may not be a carry somewhere else. Let's say we're over here. So what I've written on the top there, that here is the carry coming in from the right. And these 2 are the things we're trying to add. And I want this to work out in the way addition normally works. If all 3 of them are 1s, In that case, I want to have a 0 here and carry over. If the two of them are 1s, I just want to get a carry and a 0 and so on and so forth. Yeah, sorry, all 3 are 1s and I get 1 in carry. And it turns out, unless I've made a mistake, I believe that this actually works. So, let's go through it. Well, the easiest way is let's pretend that the right has the input from the guy to the right and 0. Now go through every possible, there are only 4 cases, 2 really. You don't have to do the 1, 0, 0, 1, but do it. First, we gotta make sure that 0 and 0 and everything 0 works. If I add 0 and 0, this I call Rx prime, which is the output, the normal output of my adder, will be 0. And it comes down here, and it goes into this adder, which gets added to 0, and its output goes out here, which is 0, and it has no carry, and that's done. And we have no carry coming out here, so the input into this adder is nothing, and there's no carry. So everything comes out 0. Great. So the first part works. Now, if this is 1, and my output is 1, there's no carry here. And I feed my 1 down and then into this adder, which adds a 0, and goes straight through and makes this equal to a 1. Now, since this is 0, there's no carry here, so this line gets nothing, and there's no carry from here, so both of these give nothing. It doesn't look connected. And do it quickly, so you know. Connected. Alright, so that part worked. 1 and 0 gave me 1 for the final result, what I want, and no carry, which is also what I want. Okay? I like to have a table of the results. It's easier to just look at it. Alright, so that worked. Similarly, if I do the B1, A0, that's the same thing as that. So we're okay so far. Now, the last case without an incoming carry is with that 1. Now, in this case, the Rx prime here, the output of this adder, the output of this adder, what's the thing this adder? The output is 0, so this Rx prime is 0, but there's a carry. So there's a 1 going into this adder here. There's nothing coming out here. There's nothing coming out here. So I'm going to This doesn't have enough output. This shouldn't be add. This should be or. I think. Yeah, I'm sorry. Oh dear. I hope it's okay. The or is in fact what I want to happen. Yeah, so nothing in here. Nothing in here. One comes out here, and since this is an OR, which takes two inputs, and there's one output, we get a carry. So that part works. Okay, so I found a bug in my system. Hopefully it's fixed. Case 2, let's suppose that there's an incoming carry. So first the zero case. Zero case, this Cx prime is nothing. There's no output coming from here. We got a 1 coming into an adder plus 0, whose result is 1, but no carry. So 0, 0 plus the carry gives me a 1, and that's what I would expect in this case. I should get a 1 here, but no carry. Okay? You guys can use this for your diagram to help. Now, if one of these is 1, what I want to happen, say if this was 1, what I expect to happen is that the result, that's this part, should come out 0, and there should be a carry. So let's see if that works. Here's an adder. There's no carry because it's just 1 plus 0. But there's an output of 1. So there's a 1 feeding into this adder. So we have 1 here plus 1. And that result of 1 plus 1 is 0. Plus a carry. This goes into the OR. So it turns into an OR. And then I get a carry. So I got a 0 result and a carry. That's what I expected. That's what I want. So therefore the 0, 1 case works, and that leaves only one more case. And if the last case works, we're done. So that's everything 1. What happened? What should happen is that we should get an output of 1 and a carry. So let's see what happens. If you do 1 plus 1, the output here will be 0. But there will be a carry. So there will be a carry coming in here, and so this will actually be a 1. Next, this is 0. So there's a 0 feeding into here, into my adder. Plus the 1 carry. So 0 plus 1 going to the adder, which is essentially an XOR, makes this into a 1. And since there's a carry left over from here that goes into an OR, we get a carry. So the answer is 1 for a carry. And there you go. You have an adding machine. All you gotta do now is just link them together in a chain. And that'll add up any number of bits in like a cascade. And that's probably exactly how they build it. Okay, thanks for watching. Bye-bye.